Hello everyone, my name is Kim Ens. I am a professor in computer science at the Institute of Information and Communication Technologies, Electronics and Applied Mathematics of the Engineering School at UC Leuven University in Belgium. In this experiment, or in this presentation, I will be presenting the result of an experiment that I conducted in collaboration with my colleagues Professor Siegfried Nijssen and Sean Pham, our ex-postdoc researcher, in the context of a recently finished research project exploring the use of pattern mining techniques to find interesting regularities and change patterns in the source code of software systems written in a variety of programming languages such as COBOL, Java, C#, and Python. In the particular experiment that we will be focusing on in this presentation, we applied pattern mining to the particular case of student source code written in Python. In essence, what we tried to do was to mine for patterns, so structural regularities in the code that were more representative for bad solutions to exam questions or to an exam question than for good solutions, and vice versa, where we define good and bad in terms of the student's score obtained through an automated grading tool that was used to evaluate the student's exams. What we hope to discover were examples of typical good, bad, or ugly coding idioms in student code, examples of prototypical good solutions, as well as possible coding misconceptions that the students may have. I will show you some concrete examples of such patterns and their corresponding code near the end of the presentation, after having explained you our mining approach in a bit more detail first. In the next few slides, I will walk you through the 5 main components of the architecture of our pattern mining framework to give you a high-level idea of how our pattern mining framework works. The first component of the architecture is an importer, which converts a source code base in some programming language into a set of ASTs or abstract syntax trees. We can either mine for frequent patterns in a single code base or compare patterns between 2 code bases, as we did in this particular experiment. When importing, there is also the option of either keeping the variable names in the generated abstract syntax trees or to replace them by a generic wildcard. In this particular experiment, we used generic variable names, so variable names replaced by wildcard, so that the code of students who answered the same exam question but using different variable names would still match the same pattern. Okay, the second component of the framework, so once we have the ASTs, the abstract syntax trees, we apply our fractals mining algorithm, which is essentially an adapted version of an existing mining algorithm called fractee, that mines for frequent subtrees in the ASTs. And we also use a chi-squared threshold to distinguish patterns that are more relevant for one code base than for the other one. So let us zoom in a bit on how that works exactly. I will not present you all the details of the algorithm. For that, I refer you to this paper which we published in 2019. But in a nutshell, our fractals algorithm will start to grow patterns in a depth-first, left-to-right fashion with rightmost pattern extension, while using a minimum support threshold to make sure that we have sufficient matches. And we also apply some additional constraints based on the minimal and maximal size of patterns, the kind of AST nodes we are interested in, and some other constraints that we added to get better results for mining in source code. And finally, after having found an interesting set of patterns, we try to grow them further to maximality. But since this growing process, growing to maximality, tends to be rather time consuming, we also use a timeout to stop the algorithm after a given allocated time budget. And then in this particular experiment, the input is not one code base, but 2 code bases. And there, the idea is that we want to find patterns which are more representative for one code base than for the other one. And for that, we use this chi-square function. So we calculate this chi-square score, and the chi-square function looks a bit like this. And the idea is that higher values of chi-square would yield patterns which are more representative for one of the code bases than for the other one. Whereas low values, like here, of chi-square would be less discriminating between the two code bases. So the idea is that we take some kind of value of chi-square, a cutoff value, and we ignore all those patterns that have a chi-square score lower. And so we just keep those peaks which represent patterns which are more representative for one code base than the other one. So that was, in a nutshell, how the pattern mining algorithm itself works. And the next three steps in our, or the next three components in our pattern mining framework are more straightforward. So there is this matching phase where we try to match the patterns found back to the source code or source code fragments where they occur. We also have a clustering step because we find quite a lot of relatively fine-grained patterns, and some of the patterns are quite similar to each other up to some small details. We try to cluster patterns that are very similar together. So they're similar often in the sense that the matches they have are quite similar. So we cluster them together, and the clustering algorithm we used in this experiment was a simple k-means clustering. So we forced the algorithm to produce only 30 clusters. Why 30? That was determined experimentally as giving relatively good results. And the final step, step 5, once we have the clusters, we will present all the results, so the patterns found, the code matches, and the clusters in a simple web interface so that we can easily inspect and browse all the code fragments, the clusters, and the patterns that were found. And this is more or less what the... Sorry, I lost my mouse. But this is what the pattern browser looks like, the visualization. You can just open it in any web navigator. And so on the left, you see the different clusters. So in this case, there were 30. You see per cluster the patterns that belong to that cluster. So the patterns would be very similar. You can also see it in the number of matches. So there's this pattern with 30 matches. There's a pattern with 40 matches here. And they essentially capture more or less the same code. There's one file extra here. And then here, for this pattern which is currently selected, you can see all the matches. The matches are correspond to files where the pattern was found. And then if you click on one of those files, you would see highlighted in yellow the part of the code that corresponds to the pattern found. In this case, the entire code is highlighted in yellow, so the entire function body here corresponds to that pattern. But this is just, in this example, it's possible that, for example, it could have been only this first statement and the return value. So it would highlight here in yellow and in red those pieces of the code that correspond to the pattern. And this allows you to quickly browse through the different patterns and get a feeling what they correspond to in the source code. I won't explain this particular example in detail now. We will see some concrete examples later on. Okay, so let's get back to the experiment. So what we did, now that we have explained the mining approach and the mining framework, is that what we wanted to do was to mine for different patterns in the score of students. Well, we wanted to mine for different patterns in students who submitted their solution to a first-year bachelor computer science exam. So it was an introductory programming course in Python. And as we said, we take two code bases as input. So we took the code of all the students participating in that exam, and we divided that code set in two code bases. The code of all the students who failed the exam, so who had a score of less than 10 out of 20, so less than 50%. And the other code base was the code of all the students who succeeded the exam. So the code of all the students who had a score of 50% or more. So we did this question by question. So per question, we created a new code base so that we could compare it on a question basis. And then, as explained before, we used this trick with the chi-square score to try to find for patterns more representative for one code base than the other. Where did this input come from? Well, at our university, in our first year programming course, the students are used to using this kind of, the tool is called Ingenious. It's an automated grader. So throughout the year, they use it to exercise their Python skills. And at the exam, we use exactly the same tool. And so it's very small here. The details are not important. We will show the details later on, but there is this tool where at the exam or throughout the year, a question is being presented to them. This is the description of the question. For example, here is the calculation and an approximation of pi. There is the signature of the function and the pre and post conditions are given, some examples of what is expected as outcome, and they have to fill in their code here. They can submit multiple times, and in the end at the exam, the last submitted version will be evaluated, and that will be their score. So how is it being evaluated? Well, the teacher, us, we after the exam, we prepare it before the exam, but the students won't see the results until after the exam. We correct their code based on a set of unit tests. The unit tests can just be based on input-output, but also we can also look at inside the code. So it all depends on how complex we make our tests. Basically, the test is a Python script, which can be as complex as we want. But essentially, the idea is we use unit test, we take the student code, and based on the quality of their code, we assign a score. And that score is a score that we take to distinguish the set of good solutions from the set of bad solution. So here is some data. For that particular exam, we had 5 questions, actually 6 because the last question was subdivided into 2 questions. You see the number of students who participated in the exam. Actually, there were a bit more than 500 students who participated. We already threw away those students who just looked at the question and didn't respond, because that would bias the result. So we only kept real responses. So real code submissions where there is some code. Empty submissions we threw away. So here in this, for the first question, for example, there were over 509 non-empty submissions, of which 470 passed the exam and 39 failed the exam. In that piece of code, we found 152 patterns. What you see in this column is the time it took for the first step, so finding the patterns, and the second step is then growing the patterns to maximality. What you do see is that growing to maximality often takes 600 seconds, a bit more, but that's due to switching between different patterns. But the timeout we used was 10 minutes, and 600 seconds is exactly the timeout. So the time we gave to the algorithm. So you see that actually we had to cut off the algorithm after 10 minutes in each of those, for each of the questions, except the fourth question. So for the fourth question, we had sufficient time to grow all the patterns to maximality. We can set that threshold higher. For example, we can take half an hour rather than 10 minutes for analyzing all those questions, but we took 10 minutes because we wanted to see how good the results were after only 10 minutes. We also tried with 30 minutes, but the results were not significantly better. It just took much more time for basically the same quality of results, which means that probably it's already grew the patterns to a good size. Okay, so these are some numbers. What is more interesting to look at is the actual patterns that were found. So what did we discover in the code of the students? I will present the results only for the first question here. So the first question was a question, like I said before, which was calculating the approximation of pi according to this series. So essentially what the students had to do is write a kind of loop where they loop over this series, calculate the nth term in the series, add them all together, multiply by 4, and return that value. So the prototypical good solution, which indeed many students found, this was the easiest question of the exam, and students tend to be good at the first question. The question became more complex near the end. So we did find 2 patterns corresponding to the expected good solution to the exam. And most matches of that pattern were indeed good matches meaning that they succeed the exam. We call this a good pattern because it represents a good solution. So here are 2 code samples. So the number 46 you see here is the pattern 46 that we found. And this is one of the code samples matching pattern 46. As we said, we use generic wildcards for the variable names. So there were other solutions that were essentially the same, but for example, not using a variable sum, but s, and they all looked very similar. Maybe the formula was slightly similar, but still correct. So the first typical solution was just using a for loop. You start summing at 0, you return the sum in the end, and here you calculate each of the terms of the series, you multiply it by 4. And you have the same solution, but using a while loop here. Okay, so this is an example of a good pattern because it captures a good solution, and most of the matches of the pattern were indeed good matches. So is it possible to also have bad matches of this good pattern? And the answer is yes. So this same pattern which I showed before, so this was a good match, there was also a bad match. So if you see here, in all the results, all the matches of that pattern, there was one student who failed. So this is weird because this is the prototypical solution, so why did the student fail? And what you see, if you look at this code in detail, the student made a mistake in the iteration variable. So he used a variable g here and a variable I here. So of course the result being calculated is not correct. There should be, well, either it should be an I here or a G there. There's some error. The student made a stupid mistake. Or maybe he didn't understand really how a for loop worked. I don't know. But in any case, he was very close to the good solution up to this variable. So you can wonder why was this match for this pattern found? We know it's a bad match because the student failed the exam. Well, the reason is because we use these generic variable names. So because we ignore the actual names of the variables, these two match to the same pattern. Yet it is interesting feedback. We can still give this student interesting feedback about his exam and tell him, like, look, you were actually very close to a solution, to the good solution that most students who did it this way had succeeded the exam. So you were not far off, but be careful next time to look at what variables you use in the loop, and that the variable name you use for iterating is the same one as you use in the body of the loop. Okay, so this is an example of a good pattern with mostly good matches and a few bad matches. So can we also have bad patterns? And indeed, we also found some interesting examples of bad patterns. What do I call a bad pattern? A bad pattern is something that represents a typical bad idiom or bad solution. And so something that we noticed, so in this particular example, was a bad pattern because the pattern captures the following structure. It captures the fact that the term calculation, so the calculation of one of the terms of this series of pi, so this would be a term calculation, and the return statement appear at the same indentation level. For those who don't know Python, you have to know that in Python, indentation is very important. For example, if this return statement would be indented here, it's outside of the loop. If it would be nested one level deeper, like here, it's inside of it's part of the loop. So a loop doesn't start with begin end. It's based on the indentation level. And since the typical good solution, let's go one slide back, would look like this. You have a for loop, and then the return statement is outside of the for loop. So it would be weird that the calculation of the term and the return would be at the same level. So intuitively, as a professor or as a teacher, you say there's something wrong if these would be at the same indentation level. So in that sense, this would be the good solution, this would be a bad solution. And indeed, for different reasons, all the students who had this calculation and the return statement at the same indentation level had wrong code. The reasons why it was wrong there were various reasons, so let's take a look at them. One student, for example, who matched that pattern had this code. There is not even a for loop or a while loop here. So he just calculates one term and returns 4 times x. There is no loops whatsoever. So clearly this is wrong. There's no loop. The second one, 2a and 2b, are two variants of the problem where there is a for loop here and there is a while loop, but there is no term calculation inside the loop. This formula should be inside the loop, and you should also increment the sum. So there is a for loop, but the for loop is not doing a lot. And here there's a while loop, but the while loop is not doing a lot. There's not any calculation nor any incrementation of this sum inside the while loop. So this is clearly wrong as well. And then the third one is very close to the good solution, but this student made the mistake of putting the return in the wrong place. It should be indented one level less. So what you see here is there is a for loop. The calculation of the formula is inside the for loop. The sum is being incremented in every step. So all this is good. The only problem is that the return statement is also part of the for loop. So which happens that if you enter this for loop, you will start iterating, calculate this term, but as soon as a return is encountered, it exits the loop and stops. So it stops the function. So it will actually iterate only once because the return is the wrong level. So the only error for this one should be that you should indent it less, and then it would have been a good solution. So in any case, this is a bad pattern, and for all these different variants, these different matches of this bad pattern, you can clearly tell the student what is going on. You should use a for loop, you should use a for loop which contains the actual formula, or you should be careful that the return statement is not nested inside the for loop. Okay, what was surprising there was actually a good match of this bad pattern. So there was one piece of code which also suffered from this problem that the formula calculation and return statement were at the same level, but the student actually succeeded the exam. So let's take a look how this was possible. So this was that student's code, still matching the same pattern. You see that here the return statement and the calculation of the formula are at the same level, but inside the loop, so in this case was a while loop, there was also again a calculation of the formula. So what this student did was calculate the formula once the first term outside, and then inside the while loop, all the other terms of the series were being calculated. And then once the loop was finished, you went out of the loop and returned 4 times the calculated value. So this code is correct, but still here. So it was a good match, good in the sense that it succeeded the exam question, but bad in the sense that it matched a bad pattern. And indeed, since there is it matched a bad pattern, you could still tell the student that even though you succeeded the exam, you could improve your code a bit. In this particular case, we could tell the student that, well, it's maybe not a good idea to have duplicated code. You see, this formula and that one are exactly the same. Isn't there a way that you could avoid having this term there by, for example, starting your iteration one step earlier? Okay, so we had some examples. I showed you for 2 different patterns, some examples of good patterns with good matches and with one bad match. I showed you an example of some bad patterns, where for bad patterns mostly the matches will be bad, but there could be good matches as well. And in that case, often you can tell still the student how he could improve his code a bit more. And we also find some monstrous code. I couldn't help but show you this one. This was also one student's solution. You see this effect is our first year students in their first exam. These students clearly didn't have the feeling of using loops. What probably happened, because you actually can see a loop here, but you see this loop also suffers from the problem of the wrong variable name being used for iteration. So probably the student started out trying this and he didn't manage to get the good results, and then started to use this trial and error piece of code, and he just hard codes all the possible calculations for I equal to 0, for 1, for 2, and the formulas just get longer and longer. Of course, this code will work for all the cases until 12, assuming his formula is correct. So he might have had a bit of score. In our case, our test suites would take random values. So I can't remember if this student actually passed the exam or not, but clearly this is horrible code. So this one also matched the pattern that we mentioned before as a prototypical good solution because of this piece of code, but it's clearly ugly code. So that's it. Conclusion. So what we did in this experiment, we tried to discover interesting patterns distinguishing a code base of good code to a code base of bad code, where the code base is given as input was the source code of students who took an exam, and good was those who succeeded the exam, and the bad code was those who failed the exam. And using an existing mining framework that was developed in earlier research, in our earlier research, the clustering came in handy. The browsing tool that we created, the browsing tool that we used in this experiment was created specifically for this experiment. We have a more advanced browsing tool, where you can also navigate through the trees, but that was a bit of overkill for this experiment. So we did find interesting examples of good, bad, or ugly coding idioms. We have to say that this is the case for this research and also for previous uses of our Python mining algorithm. It's not always easy to find the best configuration algorithm, the best configuration of the algorithm. There are so many parameters to put for the different constraints, for the timeout. We use a configuration that worked well in the past, and we tried that configuration here. We had to adapt it a bit, but as soon as you start changing the variables a bit or the thresholds a bit, the results may not necessarily improve. So tweaking to get a good set of configurations takes a bit of time. Obviously, there is more analysis needed. So now we just took one exam. We have multiple other instances of such exams. So we took the exam of January 2020. The exam is repeated with other questions every year, 3 times in January, in June, in September. So we have lots of other code bases on which we could repeat the experiment and look what other kinds of patterns are being found. We could, in a previous instance of the course, 4 years ago, the course was still in Java. So we also still have all the code and all the submissions of the students when the course was still in Java. Since our pattern mining framework can also work with Java, we could also analyze that. We haven't done it yet. So I think what we should do if we continue this research is first look a bit more at what kind of idioms we find in other Java or Python code submitted by students. And our ultimate goal or hope would be that the information, the kind of idioms we found could be useful in a more advanced recommendation system, a source code-based recommendation system that could be used by teachers to help the students or by the students themselves to get hints on what is wrong and how their code could be improved. I will leave this final slide. These are some other related scientific publications related to pattern mining, not related to pattern mining applied to student code, but pattern mining applied to mining legacy and other source code for patterns, which was the Intimals research project in the context of which this pattern mining framework was developed. And Intimal stands for Intelligent Modernization Assistant for Legacy Software. So this is in case you would be more interested in the mining aspects than in its application to education. But I guess that for this particular workshop, you're more interested in the education aspect. I thank you for your attention. If you want to contact me and for more questions, don't hesitate to email me at kim.mens@uclouvain.be. Thanks for your attention and bye.